particles come together to create a stable granular skeleton. Therefore, there has to be a minimum number of contact points for the skeleton to be stable, like a table needs a minimum of 3 legs. But it's not only just equilibrium. Particle shape plays a critical role in how different particles come together. What we are going to cover today applies to coarse grain soils. And the reason is that when particles come together and they are very fine, they feel each other by electrostatic interactions, and the fabric they create is quite unique compared to the fabric of coarse grain soils. Furthermore, for our analysis today, just to highlight the granular nature of soils, we're going to assume that particles are spherical. So let's consider the following situation. We have particles arranging themselves in a simple cubic configuration. And please recognize that I'm showing a 2D manifestation. Actually, these particles are at the corners of a cube, and therefore what you are seeing is just the front, but actually what is going on, they are here forming the corners, and this is going to be important when we proceed with the analysis. Therefore, if particles are diameter d, the cube is size d. The first thing that we can realize is how many particles is each particle touching. Well, look at this. Each particle is touching neighbors to the left, therefore to the right, back, therefore front, top, therefore bottom. Therefore, this particle is actually touching 6 particles. This is the coordination number for a simple cubic configuration is 6. Then we can begin asking questions about things that are classical in soils. For example, what is the porosity of this configuration? By definition, this is the volume of voids over the total volume. Now notice that computing the volume of that void is difficult. Therefore, we're going to replace this by the volume total minus the volume of the solids over the volume total. And this is going to be equal to, being size d, the repetitive unit, d cubed over d cubed minus the volume of the solids. Now notice that at each corner I have an octate of a particle, and there are 8 particles in this simple cubic repetitive unit. Therefore, I have 8 octates, so it's 8 over 1 over 8 octates of the volume of a particle, which is 4/3 pi d cubed over 8 r cubed. The first conclusion from this analysis is very important. It doesn't matter whether this is the configuration of atoms in a simple cubic packing of sodium chloride crystals, the sodium chloride atoms to form table salt, or this is a simple cubic packing of boulders. In this very loose configuration, the size of the particles cancels out. The porosity is particle size independent. And it turns out that this is going to be 1 minus 8842 pi over 6. And this is equal to 0.47. I apologize if that came out of the screen, so let's write it again, 0.476. We have many other questions that we can ask. For example, if I look at that configuration, what is the largest particle that could fly through? If it was just a single particle, I'm looking at the size of that central particle. Well, I can apply Pythagoras, and so if these sides are each of them size d, the diagonal is square root of 2 times d, and the particle is going to be the diagonal minus 1 radius and 1 radius. Therefore, the size of the particle that can fly through is equal to d square root of 2 minus 1, which is 1.41 minus 1, 0.41, the diameter of the large particles. This is the foundation for filter criterion. In other words, the finest particles that can fly through a simple cubic packing configuration is slightly smaller than the diameter of the particles themselves. There is a caveat, though. If I have two particles and the smaller particles go through, if there are many of them, they may be able to form a bridge. And so they will clog the pore throat. And so in order to really go to filter criterion, I will have to probably take this diameter divided by 4 or 6, depending on the particle roughness. But this is, once again, the foundation of filter criteria. We can ask other questions. For example, now this was the particle that could fly through. Now I would like to ask, what is the largest size of the particle that can fit in the voids of the simple cubic packing? Now, to do that analysis, we have to really think in 3D, because I'm looking at the heart of the simple cubic packing. So it's not just at the diagonal on the front face. It's really going to be the diagonal that joins completely opposite points. So I'm looking at that diagonal that goes across. Now the size of that diagonal is this d gave me this main diagonal, a square root of 2. But now this one is also normal angle with respect to that size, which is also d. So is square root of 2 squared, which is 2, plus 1d is 3. So the size of the main diagonal is a square root of 3d. And so the particle, the largest particle that can fit in, is equal to the particle diameter square root of 3 minus half a diameter and half a diameter minus 1. And so this is the largest particle that can fit in. And now I have one more question. If I manage to put this particle in every single hole in a simple cubic packing, then the question will be, what is the mass of these fine particles that fit in with respect to the mass total? This is grain size distribution. I could ask other questions. What is the porosity of the simple cubic packing with the particle that fits in? So I have to subtract in the upper equation, I have to also subtract the volume of a small particle, which is completely in, and you will see how dramatically the porosity decreases. I could also ask, what is the coordination number now that I have put a particle inside? And so let's compute that one. This particle at the corner will be touching, in addition to one above, below, left, right, forward, and backwards, it will also be feeling one small particle at the top on each of the corners. So there will be four more contacts at the top and 4 more contacts at the bottom. So the coordination number will become equal to 6 plus 8 will be 14. And now something very important has happened. By being able to position particles inside other particles, I have dramatically reduced the porosity, I have changed the grain size distribution, I have changed the coordination number between particles. There will be much more friction trying to shear this, and because the packing density has become very high, any shear, particles will not be able to fall in the voids, particles will have to expand. So I have decreased the porosity, and I'm going to cause an increase in dilatancy. Furthermore, imagine a water molecule flying through, or don't even need to think at the atomic scale, molecular scale, you can think of just water flow. Water flow going through these pores, these are large pores. But as soon as there is a particle inside, now water will have to really bend around, and furthermore, there will be lots of surface to rub against and to experience drag, which is going to slow it down, which means the permeability will decrease dramatically. So exercise for you. Please repeat these computations. Complete the numbers that I couldn't remember. Check the values for the grain size distribution and the porosity when you fit a particle inside. And then, if you saw there, let me invite you to think that while we did all this for simple cubic packing, which is very easy to visualize, now let's assume that you started with a cubic tetrahedral packing, which was significantly denser to begin with. So now, how would you extend this analysis for cubic tetrahedral packing? And ask yourselves all the questions all over again. What is the coordination number? What is the porosity? What is the largest size of a particle that you can fit in the voids, or that can fly through the pores? And if you manage to fit a particle inside, what will be the impact it will have on the porosity, the coordination number, and the grain size distribution? You may think that these analyses are not that convenient for engineering purposes, but this is the foundation for so much understanding of soil behavior that we propagate thereafter into our engineering analysis. Above all, it reminds you that soils are granular materials.